So we'll study electric potential. What is electric potential? Let's start with the general concept. See, if we have field lines of what? Field lines of force. Let's say there's some force and these field lines are because of this force. You know about force in, you must have studied in mechanics. So, and if we have a particle at infinity, that is very far from this, and we have a point in this region, of field, we have a point P. We want to know the work done in bringing a particle of mass m from infinity to this point. If you remember, this is gravitational potential at this point. This is the definition. So if this force is F, obviously we'll have to apply an external force to bring this particle to this point. And work done, we know work done is what? It is F external into distance. This, if this be R, then this. Or what we do? We take small distance and integrate it from infinity to this point P. This is our approach. Better to say this is our better approach. F into dr, and then we integrate it from this to this, and it is independent of the direction, not direction, it is independent of the path. This is what you call conservative force. You must have studied conservative force, that it is dependent on this point and this point only, not on the path, whether it has come through this path or directly or like this. So in a conservative field, the work done is this, and if you talk of this force, obviously this force will be equal to this external force in magnitude. The direction will only be opposing, so it is minus F because of this F in F dr from infinity to this point P. This is work done. This you know. This you have, all of you must have studied mechanics, all of you must have studied work, energy. So now let's bring this concept to electric fields. You know, electric field, we have field lines for electric field, and we have a force on a charge if placed in that field, that will be QE. So if an external point, let's say it is at infinity, if a charge Q is brought to this point P in this field, obviously you'll have to apply external field and work done will be there. So work done will be what? Work done will be F external into distance infinity to P, this point. Same. This is the work done in bringing charge Q. Okay. Now, next, instead of an external electric field, you can also say, if we have a charge Q, because of this, we'll have force, we'll have electric field. Let's say we want to know, this is point P, what is the work done in bringing a charge small q from infinity to this point. So that will be this only, and if you use F external here, it will be equal and opposing to the force due to this. Force will be 1 pi 4 pi epsilon 0 q into q by, if this be r square, I am using magnitude only. Clear? So this will be minus infinity to P F dr. This is the work done in bringing this charge from here to here. What if this charge is a unity positive charge instead of any charge? What if this is plus 1 volts, 1 coulombs? Then force will be this. This is force, and you can write it like this, minus infinity. Let's say this is r. So minus infinity to r, 1 by 4 pi epsilon 0 q by r square dr. This is what? This is the work done in bringing a unit positive charge from infinity to a point P in an electric field. Electric field means because of which we are, the charge experiences a force. So this expression gives the work done in bringing a unit positive charge from infinity to a point P, which is r distant from a charge Q. This is called the electric potential at this point. That is, work done in bringing a unit positive charge from here to here is its potential. So you can write it as Vp, that is potential at P. And what will be the work done in bringing Q charge from there to there? That will be Q into Vp, because Vp is for unit positive charge. So if the charge is Q, the work done in bringing that Q charge will be Q into Vp. So you get what is electric potential, the definition. So the definition, according to the definition, it says work done in bringing a unit positive charge from infinity to a point, let's say P, in an electric field, or due to Q. We are taking electric field due to Q. This is your potential. This is the definition of potential. Therefore, work done in bringing Q charge will be Q into V. This is clear for a unit charge. Let's get the result. This will be equal to minus Q by 4 pi epsilon 0. And what is dr by r square? That will be minus 1 by r. So minus cancels, 1 by r. This is what? Infinity and r. 1 by infinity will be 0. So what you get is Q by r 1 by 4 pi epsilon 0. This is the electric potential at this point P, which is r distant from the charge Q. Clear? This is, we have deduced expression for electric field at point P, not field, electric potential at P due to a charge Q r distant away from it. Okay, so if this be in vector, you have r cap here, if this is the direction. Okay, clear? So you can see potential varies inversely to r. V, we denote potential by V. So V varies inversely to r, whereas electric force varies to r square. Clear? So I think you must have understood what electric potential is. Again, I am giving the definition. The work done in bringing a unit positive charge from infinity to a point in an electric field is the electric potential of that point. Okay, so if this is Q and we are talking at r distance, this is, let's say, V. This means if this is charge Q, then in every direction at distant r, the magnitude of this potential will be same. Not the direction, but magnitude of this potential will be same. That is, we'll have, this is, or all the points on this circle or on this sphere, we are talking of 3 dimension. In all directions, you have electric field because of this Q. And so, at distant r, on that sphere, at let's say the radius is r, the potential, the magnitude of potential is same. That is called equipotential surface. Equipotential surface. Okay. So for charge Q, it is like this. If it was an electric field, uniform electric field like this, let's say this is the case, then at this point, all on this line, electric field of the potential will be same. So this is, these are also equipotential surface. Clear? Now, what is potential difference? Potential difference. I told you the potential at point P is Vp. Potential at point, let's say another point R is Vr. Then, if, let's say, because of this charge, this is P and this is R. This is R1 and this is R2. Okay. Now, work done in bringing a unit positive charge from here to here is to P, F is due to Q into dr. This is the work done, that is the potential at point P, minus this, minus becomes plus. So minus this, infinity to R, Fq dr. That is potential at this minus potential at this. This is called the potential difference. That is, this is Vp minus Vr. Okay. So if 2 points have different potentials, there will be a potential difference between the two. Okay. What about equipotential surface? They have equal potentials. So the meaning is, if you take a charge from one point to another on equipotential surface, since this and this is equal, the work done will be 0. So on equipotential surface, work done is 0, because that will be Q into V, where V is 0. Okay, potential difference is 0. So work done will be, what will be work done? Work done will be Q into V. That is the difference between the two. If we say Vp, then this means work done in bringing Q from infinity to point P. But when we say between P and R, then the difference between, potential difference between P and R into Q will be work done. But when we talk of equipotential surface, this will be 0, so work done will be 0. This you should understand. So if you want to understand in numbers, the potential is 1 by 4 pi epsilon 0 into charge by distance. This you know is 9 into 10 to the power 9. Let's assume charge is 1 coulomb, though this is a very big charge, but let's say it is 1 coulomb. And let's say we want to know at 9 meters, what will be the potential. So put it here 9, you'll get 10 to the power 9 volts. The unit of potential is volts. Okay, so this is how we calculate potential. Second, if let's say we have a circuit, this is a voltage source, this is a resistor, this is another resistor, this is, let's say, another battery, then another resistor. So this is one point, equipotential surface, this is another equipotential surface. Let's say this is A, this is B. If potential at A is 10 volts and potential at B is 5 volts, obviously this minus this, that is potential difference between A and B. A and B will be V at A minus V at B, that is 10 minus 5, which is 5 volts. So the potential difference is 5 volts. You can directly find the current. When you know voltage, you can find current. So this is the meaning of potential difference. Okay. Now let's see what is the electric potential due to an electric dipole. We have Q plus Q and we have minus Q. So this is a dipole. This is its center. Let's say we have to see at this point. This is the point. Okay, which is r distant, or the position vector is r from this point. This is from here to here, it is r1. From here to here, it is r2. These are vectors. This is a, this is a, 2a. The distance between the two dipoles is 2a. So what we are seeing is potential due to dipole at this point P. Okay, we know that, see, because of this, V due to plus Q will be 1 by 4 pi epsilon 0 Q by R1, and potential due to Q2 will be, this is minus, so minus 1 by 4 pi epsilon 0 Q by R2. These all are in vectors. Okay, let's say this angle is theta. So first of all, let's write what is the net potential at this point due to these two. It will be this minus this. Okay, or we can take this common, Q by 4 pi epsilon, then 1 by R1 minus 1 by R2. This is the potential at point P. Now let's resolve it into, in terms of A and theta and R, because we know it is R from the center of the dipole. We'll have to resolve R1 and R2 in terms of A, R and theta. What is, if you know vector, and you must know vector when you are studying electricity, you must know vectors. So R1 will be what? R1 square will be R square plus A square minus 2AR cos theta. Okay, why? Because R is the hypotenuse. though not hypotenuse because this is not a right angle triangle, but you can resolve it by dropping a perpendicular and then you can see what is the value of this line. Okay. Now R2 square, this one here, this you'll have to drop perpendicular for R. So if you resolve it, it will be R square plus A square plus 2AR cos theta. This is geometry. Or I'm working on one, the other will be just minus and plus, the difference will be minus and plus only. So this is, if you take R square out, it will be 1 plus A square by R square minus 2A cos theta by R. For the second one, that is R2, this will be plus, nothing more. Now let's suppose that R is greater than A. We know for dipoles we take distances that are very large in compared to the distance between the dipoles, between the two charges. So our case is R is greater than A. In that case, this will be almost equal to 0. So what we can say, this is simply 1 minus 2A cos theta by R, and R2 will be R square 1 plus 2A cos theta by R. Clear? Now this is R1, not R1 square. So R1 will be under root this, that is, this will be R and then minus half of this. Okay, root over this, not minus half, this will be half of this, root over this. Okay, so here what you will have, you will have 1 by R and this. Okay, so if you take 1 by R out, you will have this in the numerator, that is, this will become, okay, let me do this. You know what is this? We can write it as q by 4 pi epsilon 0 and we can take R common, so that the first one will be 1 minus 2A cos theta by R to the power minus half minus 1 plus 2A cos theta by R minus half. Okay, this is what we get from this expression. You know expansion, minus half. Simply what we do, we put it here. So this becomes plus, and that is, we multiply this by, we expand this, binomial expansion. So this will be 1, because of this minus, this will be plus, and half multiplied by half. So this is 2. So this will be q by 4 pi epsilon 0 R. This will be 1 plus A cos theta by R. Okay, what about this? This will be 1, because of this it will be minus, so minus A cos theta by R. See, 1 cancel, and this is 2A cos theta by R, 2A cos theta by R. So what we get? We get 1 by 4 pi epsilon 0. Okay, then what is q into 2A? Charge into the distance between the two. This is dipole moment, and when you multiply it with cos theta, what you do? You actually take P dot R vector, that is vector in the direction of this. This is P R cap. So this becomes 1 by 4 pi epsilon 0 P R cap by R square. This is the potential at point P due to an electric dipole, where R is the position vector from the center of this dipole. This is the formula for, or expression for, the potential due to an electric dipole. And this is from minus to plus, you know about this moment, and this is P dot R, I forgot. P dot R cap, R cap is in the, it shows the direction of the position vector. This is moment, dipole moment, this is R square. So this is, you know, unique. Potential varies proportional to, inversely proportional to R square when you have dipole moment. Clear? So potential due to dipole is clear to you. These things will be more clear or crystal clear when we'll be solving some examples. For now, let's understand different concepts. What will be the electric potential due to a system of charges? Due to a system of charges. What is the meaning of system of charges? It means we have more than one charge. Let's say this is Q1, this is Q2, this is Q3, this is Q4, and we want to know what is the electric potential at this point P. Okay, this is the point P. What is the electric potential due to this system of charge? Let's say this is 1, so R1P is the position vector for this. This is Q2, R2P, and so on, R3P, R4P. So potential will be what? It will be 1 by 4 pi epsilon 0 Q1 by R1P plus 1 by 4 pi epsilon 0 Q2 by R2P, and so on. So this is the potential, electric potential at a point due to a system of charges. That is, they all add up. What you have to do is find this. If you find the position vector R, which is equal to R1P plus R2P and so on, and that is if this is the point from where you can assume that all the charges are concentrated. All charges are concentrated, and this is R simply. That is, R is R1P plus R2P plus R3P and so on, and Q is, what is Q? Q is Q1 plus Q2 plus Q3 and all the charges. Then this is simply 1 by 4 pi epsilon 0 Q by R. Okay, clear? Now we have been talking of electric field and we have been talking of potential. What is the relation between electric field and potential? What is the relation? Let's understand what is the relation. Let's say this is electric field. Okay, now we have this, the potential of this line is V, and we move a distance, let's say del L, and the potential changes to V plus del V. Okay, that is, in this electric field E, we move from here to here, the potential changes from this to this. So what is the work done in moving a unit positive charge? Work done in moving a unit positive charge in this field, it is equal to potential at this point minus potential at this point, that is V minus V plus del V, that is minus del V. Okay, and we know that work done is equal to electric field, the magnitude of the electric field into this length E into dl for a unit positive charge. So if you equate these two, what you get? You get E is given as minus del V by del L. So this is partial differentiation, because the potential may depend on certain other variables also. So partial differentiation of V with respect to length is electric field, and this gives the potential of the electric field, or the electric field is in the direction in which the potential difference is steepest. So this is the meaning, and the magnitude of this is potential per unit length. Clear? So this is the relation between E and V. So when we'll having function, we'll take partial differentiation and we'll get the electric field. So what we saw, that electric field is the magnitude of electric field. Instead of putting an arrow over this to show that this is a vector and then modulus, I'm just writing E. So I told you this is del V with respect to del L, the length. Okay, or you can, if you have electric field in x, y and z direction, this you can write as d del of V with respect to del of x in I plus del of V with respect to y in j and del of V respect to z in k. Okay, these are unit vectors, and from here you can write V is what? V, that is the potential difference between 2 points, is E dl minus, that is, you can write it in this way. V, the potential difference, will be equal to minus E x component of E dx from, let's say, x1 to x2, then y component from y1 to y2, that is ey dy, and finally you have z1 to z2, ez dz, where your electric field E, I'm writing it here, E is what? It is EXI, EYJ and EZK. Okay. So this you should keep in mind. We'll now see some problems, see some examples to understand how we find out electric field intensity and how we find out potential difference by using these relations. So this is a question. Electric field is given as 3I plus 5J, and we have to find the potential difference VA minus VB, where the position of vectors of A and B are, RA is given by I plus 2J and RB is given as 2I plus J plus 3K. How we'll do? I told you how we find potential difference A between A and B. It will be equal to E dl, that is equal to Ex dx plus Ey dy plus Ez dz. The limits are from x1 to x2, from y1 to y2, and from z1 to z2. Now, if you look at this electric field, Ex is 3. So it is 3. The limits are from, see, x1 to x2. In the x direction, it is from 1 to 2. So from 1 to 2, and we have this as dx plus y1. First of all, what is Ey? Ey is 5. I'm taking it out, Ey. And then y1. y1 is 2 and j is 1. So it is from 2 to 1. And we have dy. What about z? See, we don't have electric field intensity in the z direction. So it will be 0. So this is up to this only. What we get? We get 3. This will be 3 x 1 to 2 plus 5 y 2 to 1. Clear? I'm rubbing this. So what do we get? We get minus 3 into 2 minus 1, that is 1, plus 5 into 1 minus 2, that is minus 1. So what is it? It is 3 minus 5. 3 minus 5, that is minus 2. So minus 2 minus, it will be 2. So it is 2 volts. Okay. So this is the way we find electric field intensity. We have used a very simple expression for electric field. We'll use function to understand it in a better way. Let's see some other examples. So this is a question in which your electric field is has x and y as variables, and we have to find potential difference between A and B, where A is given and B is given. Now we know that dV is equal to minus E into ds, that is x y z. So what we can do, we can put it like this: 3x square yi plus x cube j into, what is it? This is xi, sorry, not xi, dxi plus dyj, and we don't have any k, so we can omit it. What do we get? We get, see, 3x square dx plus x cube dy. So dv is equal to this. If you see it closely, this is basically derivative of x cube y. If you take this, it will be, first of all, with respect to x, then 3x square y dx, and then x cube dy by y, so 1. So this is derivative of this. This, if you expand this, you will get this. So now our v will be minus from 0 0 0 to 1 1 1. Okay. So this is minus, it is like, say, d theta, so it will be theta only. So x cube y, the limits are 0 0 0 to 1 1 1. So we put 1 1, so it is 1 and then minus 0. So what we get? Minus 1. Finally our answer will be minus 1 volts. V will be minus 1 volts. Clear? See, this is 1 because you put x equal to 1 and then y equal to 1, so 1, and then minus 0 0. So 1 minus 0 is 1. So we get minus 1 volts. That is the potential of B, potential at point B is higher than potential at A. B is given as x into y square minus 4x square. We have to find electric field. What is E? You know, it is minus V by, if you have x, you have x and y and z components. So del V by del x minus plus del V by del y plus del V by del z k j I. This you know. So we'll put it del V by del x. What do you get? See, V is equal to x y square minus 4x cube. Okay, so del V by del x, what you will get? You will get y square minus, what's here, 12x square. So you get here y square minus 12x square I. Then what about y? When you take with respect to y, del V by del y, it is 2xy, then here it is 0. So you get 2xyj. Del V with respect to del z, you don't have any z variable here, so that will be 0. So this is the electric field. Okay. Now we have a very interesting question. It says this is a plus q at the origin, and we draw a circle. Let this be radius r, and on the radius of this we have 2 points A and B. What is the work done in moving a charge, let's say plus q, from this A to this B via this circumference? What is the work done? See, work done is, you know, q into V. This you know, work done is q into V, but since the charge is here and this sphere of R, it is equipotential surface, so the voltage difference between A and B will be 0. So what you have? Q into 0, that is work done is 0. Okay. The second part is, what will be the work done if the charge is taken from here to here and then from here to here? Okay. Again, charge is first taken from A to C and then C to B. Whatever B, ultimately what you have the potential difference between A and B. Work done will be Q into this, and this is 0. So work done will be 0. So this you should understand.